so we started talking about binomial random variables. These are random variables that are kind of like what we did before with the probability distribution and finding probabilities, but it's a very specific situation where it has to fit certain guidelines, right? So we did an example last class where we played Squid Game, and we had to roll our die 7 times, right? So we had 7 trials. Every single time we roll our die, we hope that we didn't get a 3, right? So we have an idea of success and failure. If we get a 3, then that's a failure. If we don't get a 3, that's a success, right? And the good thing about this situation is the probability that we succeeded was always 5 out of 6, because every time you roll a die, it's always 5 out of 6 of not getting a number, right? So the whole idea of a binomial random variable is we're counting the number of successes, or every time we don't roll a 3, in a total of like a fixed number of trials, okay? And I kind of wrote out these rules here. The hardest part of a binomial random variable is trying to figure out if it is one or if it isn't. At least that's how I think of it. And I wrote out 4 rules that things have to follow, okay? If you're looking at a situation and you're trying to see if it's a binomial experiment or not, the first thing you have to do is check to see if there's a fixed number of trials. So before you even roll the die, you have to know how many times you're rolling the die. You have to know how many times you're doing a thing for it to be binomial. Number 2, we have to have an idea of a success and a failure. Even if there's multiple things going on, there has to be something that is good or a success, and another thing that's the opposite of it. Okay, so we can't have multiple things going on, only success and failure. Number 3, the probability of getting a success has to be the same every time you do it. For example, with the Squid Game example, the probability of not getting a 3 was always 5 out of 6, no matter how many trials that we had. Every single trial was the same probability. So that's a big thing with binomial experiments. The last thing is that the trials have to be independent. Okay, so if I roll a die once, does that affect what happens the next time I roll a die? If we have independent events, every single trial is independent of each other. So what happens on trial 1 doesn't affect what happens on trial 2. Okay, so as long as we satisfy these 4 properties, then we have a binomial random variable. Jason, do you need a set of guide notes?
No, I have.
All right. All right, so I think we left off last time on determining if something was binomial or if it wasn't binomial. We did a couple examples. Let's just do a few more, okay? I think we left off on number 3. Okay, and number 3, we have 10 cards. Okay, and all these cards are in a box. Okay, 5 of these cards are red and another 5 of these cards are green. Okay, what I'm doing here is I'm going to take 3 cards out of the box at random. And it's not really said here, but what's implied when it says 3 are drawn at the same time is every time we draw a card, we don't put it back. Okay, so I draw out a card, I don't replace it, and then I draw out another card, I don't replace it, and then I draw out a 3rd card and I don't replace it. That's what's going on. Okay, let's go through the steps to see if this is a binomial random variable or if it isn't. Well, the first step asks us, okay, do we have a fixed number of trials? Well, do we have a fixed number of trials in this case? Yeah, right, how many trials are there? There's 10, right? Because, oh, sorry, not 10. Sorry, there's 3, right? You guys said 3 and I said 10. There are 3 trials because we're taking 3 cards. So whatever the trials are, they're every time you do something, right? So if I'm taking out a card, or if I'm rolling a die, or if I'm flipping a coin, that's a trial. In this case, we have 3 trials. And remember, we called that n. So n equals 3. This doesn't change, so it's fixed. We're good with number 1. Okay. Number 2 talks about the idea of a success and a failure. Usually you can tell what a success means by looking at like the last sentence in the paragraph, because it tells you what we're interested in. So taking a look at our situation here, what do you think is a success? Red card, right? Because it says X is the amount of red cards that are drawn. Whatever X is describing, that's what a success is. So in this case, a success is drawing a red card. Which means, I guess if we fail, it's not red or green, right? So in this situation, there's a really clear idea of a success and a failure. So we're pretty good on that. All right, let's go to the, let's skip the third one for now. And let's check the fourth one. Okay, and I'll tell you about the third one after. Okay, the fourth one talks about this idea of independence. Does one trial affect the other? Any ideas on if we have independent events this time? Kate?
Because if you don't replace it, then the probability changes. So if you have a likely increased likelihood of drawing a green card if you previously drew a red card.
Yeah, that's perfect, right? So let's say I have my box, 5 red, 5 green. The first time I pick out a card, it's a 50-50 chance, right? So if I, for example, draw a green card the first time, it's a 50-50% chance. If I don't replace that green card, now my box only has 9 cards. And the second time I do a trial, the probability of getting a green card and a red card isn't 50-50 anymore, right? Because the number of cards in the box are changed and the amount of each one is different, okay? So in this case, the first time I go about picking out a card is different than the second time I pick out a card. So we don't have this idea of independence. We are not independent. Because trial 1 is definitely going to affect trial 2. What I get for trial 2 is going to affect what I get for trial 3. So a good hint that something's not independent is whenever you're picking out a card and it doesn't say that you replace the card, okay? If you replace the card, things are a little bit different. But if you don't, then it looks like we don't have independent events, okay? Which means number 4 doesn't work, okay? And if one of these doesn't work, it's not binomial. And I cannot spell binomial, so not binomial, okay? This is a sad face, okay? I also could have said it didn't satisfy number 3 because, well, if we don't have independent events, it kind of automatically makes each of the trials have different probabilities, okay? So unless you do things in a very specific way, number 3 is not going to work out. I think determining independence is a little bit easier than determining if the probability is the same every time. Okay. Let's do number 4. We have a bag. It has all these balls in them. They're red, green, and blue. Okay. I'm going to take 10 out of the bag at random, one at a time. And this one's different than number 3 because once I take something out of the bag, I'm going to replace it immediately. And then I'm going to do my next trial. Okay. We're going to record the number of green balls that we have. Okay. Number 1. Do we have a fixed number of trials? See some nods. How many trials do I have? 10, right? Every time you do something, that's a trial. So if I take 10 balls out of the bag, there's 10 trials. So it looks like that is fixed. We are good. Number 2, we need an idea of success and failure. What would success be in this situation? Yeah.
Getting green balls.
Getting green, right? We're interested in the number of green. The last sentence in these paragraphs tells us what we're interested in. The idea of success is getting green, okay? Which means a failure, well, there's other things that could happen, but all we're interested in if it's green or if it's not green, right? So a failure would be not green. Okay, so if we have that idea of success and failure, we are good. Number 2 is good. Number 3 asks us about the probabilities. Are the probabilities for every single trial, is that going to be the same? Do you think the probability of each trial here is going to be the same? Here's some nods, right? It will be the same, right? Because if I'm replacing each of the balls every single time, the chances of me getting a green ball is going to be the same, whether I'm doing trial 1 or trial 9, right? Because I'm putting things back to where they were originally every single time I do a trial. So we actually are done number 3, and number 4 talks about independence. Are these guys independent? Yeah, right, because if I'm replacing the ball, so whenever you have this word replaced immediately, that's a good chance that number 4 is also satisfied because what we have independent events, it looks like we're putting things back to where they were in the beginning. We're good for number 4. We've satisfied all the 4 properties, which means, yes, this is a binomial experiment. Okay, so it gets a smiley face. Any questions on 3 or 4? All right, let's do number 5. All right, number 5, we have a coin. We're tossing it until a head appears. X is the number of tosses that we're doing. I'm going to tell you that this is not binomial. Okay. Is there anyone who can explain which rule it doesn't fit in? The first one. And why does it not fit the fixed number of trials? And yeah, right. So it doesn't tell us like, oh, we're rolling the die 10 times, or hey, we're tossing a coin 15 times, or we're taking 10 balls out of a bag. That doesn't happen, right? So if it doesn't tell you a fixed number of how many times you're doing the experiment, that's not binomial. It doesn't fit number 1, okay? There's no value that we can set n to. Now, n describes how many times we're doing something. I can toss a coin twice until a head appears, right? Or I could toss a coin 7 times until a head appears. So that's not fixed. There's no set amount of times that I know I'm gonna toss the coin until a head appears, okay? So this is actually not a binomial experiment. Gets a sad face. It doesn't satisfy number 1. All right. Any questions on determining if something's binomial or not binomial? I think we're pretty good on that. Okay, that was the hardest part of this entire situation. After we do this, all we're interested in is actually trying to calculate probabilities when we're dealing with a binomial distribution. In this class, we used to teach everyone how to like manually do it, like using calculators in our hand. I'm going to tell you that is a very not fun way of calculating probabilities. What helps us a lot in this class is Minitab. Okay, and Minitab will help us a lot because it'll give us something that we're used to seeing. Okay, so I'm not going to tell you how to calculate it by hand. It's just going to take way too long and no one likes doing it. I'll give you the instructions for Minitab and I'm going to run through it for one of these questions so you can see what to click. Okay, now it's not too bad. I promise. When we get to more different probabilities, you'll get used to typing things into Minitab. But let me show you what you're supposed to do before we get into like all the instructions here. Let's flip our page over. Okay, in this example, we have the Pew Research Center, okay? And they said that approximately 30% of the internet users in the US use the image sharing website Pinterest. Wow, this question was written a long time ago. Okay, we wanna take a simple random sample of 8 internet users and we're using the binomial probability distribution to calculate the probabilities. If the question says binomial in it, we don't really have to wonder if it's binomial or not because it's telling us it's binomial already. So we already know this is a binomial distribution. All we have to do is plug things into Minitab and figure out what the probabilities are. Before we do that, let's like actually figure out what we're going to type in, okay? Now, let's think about this. For a binomial random variable, we need to know a success and we need to know failure, right? What do you think a success would be here? So what are we interested in? Perfect, right? Using Pinterest, right? If we're interested in how many people are using Pinterest and it gives us like a percentage for it, that's what we're interested in. So in order for something to be a success here, someone has to be using Pinterest. So using Pinterest. And in this example, we're just counting how many people are using Pinterest, okay? Now, N represents the number of trials that there are. Looks like we have 8 people. Well, that's the number of things that we're interested in. We've got 8 trials, okay? Now, probability, usually the question just gives us what the probability is. It's a 30% chance of being a success or using Pinterest. So I know my probability is 30%, okay? Now, one really important thing when we're using Minitab, Minitab does not like percentages. None of the software that we use in this class even the textbook doesn't like using percentages. So if the question ever gives you a percentage, I want you to always change it into a decimal. Okay, so always change 30% into a decimal or 0.3. Okay, if you type in 30% into any of the software that we use, it's just going to kind of freak out and give you something wrong. So 0.3 is what we're using. All right, let's go through these steps in Minitab. You can kind of follow along using the back page here that tells you all the steps. And let me show you what I would click through if I were to do this question. Okay. So I've got Minitab set up here. Got to put this up here. All right. And looking at number or step 1 in my list of things, find out what NRP are. We figure that out on our notes. So we did step 1 already. Step 2 says enter the numbers 0 through n under column 1, which means I need to like type stuff under here, right? So basically what that says is we said that n was 8. If n is 8, I'm going to type in the numbers 0, 1, 2, 3, all the way down to whatever n is or 8. So I'm just going to do 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so that's all that step 2 is asking us to do. Just typing in 0 all the way through n under C1. All right, so you're done doing that. All right, step 3 says click on calc, click on probability distributions, and then click on probability density function. We'll learn what this word actually means a little bit later. For now, just this is the Minitab thing that tells us what to do. So probability density function. All right, we're on step 4 now. Step 4 says make sure the form of input says a column of values. That's not what it says, so I'm going to go and change it to a column. Okay. Under values in, it says double click C1. So I'm going to double click that. And then under distribution, it has to say select binomial. Right now it says normal, which is a different distribution that we'll talk about later. Okay, so I'm just going to click this and change it to binomial. Okay. Here it'll tell me the number of trials. Remember, the number of trials is 8 because that's what n is. And the event probability is telling us what p is. So I'm going to type in 0.3, which is what we said in the question. Next, under output, just make sure it says display a table of probability density values. Looks like it has it there. So I'm just going to click OK. All right. And what you get up here is a chart that looks really similar to our quiz, right? So this is a probability distribution. It just shows us all the things that can happen and the probabilities right next to us. So once we have this, it's super easy to calculate probabilities because we know how to do things that look like this. Okay, so we're just back to what we normally did. Any questions on how I use Minitab here? Okay, the instructions are in your notes. You do have to use this for your homework. So just make sure you have this packet with you when you're doing your homework so you know what to click through. All right, let me go back to this situation here. All right, I love using my iPad, but it gets annoying switching back and forth. There we go. All right, once we're here, we can answer questions just like we normally do, okay? For example, if I wanted to find the probability that exactly 4 of the people used Pinterest, what would that probability be? Kind of like on your quiz, Kate? Yeah, perfect, right? You just go to 4 on your chart and the probability is right there. So if I want to know exactly 4 people using Pinterest, it's literally right there, 0.136137. And that's all you have to do. Same thing you've been doing on your quiz. Part B, if I wanted to find the probability that 3 or fewer use Pinterest, how would I find out this one? Yeah, add the probabilities between 0 and 3, right? If it's 3 or fewer, it includes 3. So I'm just adding up these 4 probabilities together. So I would add, and I know these numbers are long. How about this? Well, I'll just do all of them. 0.0576, 0.19765, 0.2965. I don't even know. 0.2541. Okay, and that gives me 0.8059. Okay, so what I did here is I rounded all the different probabilities to 4 decimal spots and I added them together. This would be good if I wanted my final answer to be accurate up to 3 decimal places. So if you want your answer accurate to a certain number of decimal places, just add on a decimal to how much you're interested in when you're doing the actual calculations. Okay, so if I were to round my answer to 3 decimal places, it'd be 0.806. Okay, and that'd be really accurate because I added on an extra one, so I have some extra precision here. Okay, any questions on part B? All right, moving on to part C, I want to find the probability that the number of people is not 2. Any ideas on how to do this one? That's a good one, right? I can add up all of these guys. So I can add up, let's see.
Or you can subtract.
Yeah, I was thinking subtract. So Elijah at first was like, okay, I can add up every single one of these except for 2, but that's going to just be torture. I don't gonna have to add up every single one of those big numbers. Another thing you can do is if it's an opposite situation, like not 2, just do 1 minus the probability of 2. So 1 minus 0.2965 gives me 0.7035. Okay, and that would be my answer for first. Okay. Any questions on example 1? All right. If you flip your page, you'll see example number 2. Okay. And in this example, we're talking about a basketball player. What I want you to do is fill in the chart. I went through on Minitab and I did all the stuff so you can just see what pops up on Minitab here. And I want you to answer A through C. To save us some time here, you don't have to add up the full number. If you want to round to like 3 decimal places or 4 decimal places, go ahead and do that. Don't do the full numbers. In this example, we have a player having a 60% chance of making a free throw, shooting the ball 6 times. I didn't really, it's kind of hard to explain why this is binomial. Let's just say the question told us it was binomial, so we don't have to check all those steps, all those 4 properties like we did in the beginning of class. All right, so in the beginning, we have a chart. I forgot who wrote this one. Maybe I just have a bad memory. That's all right. Well, whoever wrote it up, I'm not gonna have you explain it because, well, success is making a free throw, right? Because whatever we're interested in is, well, what we're given the percentage of. Okay, so we're interested in how many times we make a free throw. Looks good. Shooting the basket 6 times means we have an amount of 6 trials. Oh my goodness. And I like how we express the event probability or the probability of making a free throw as a decimal instead of like the question giving us a percentage. All right, let's pretend I went through Minitab. I went through all the instructions and I got this distribution that tells me the probability of making 0 through 6 free throws out of all of the 6 trials. Okay. And let's see what these questions are asking. The first one wants to know, okay, what's the probability that he makes exactly 3 out of the 6 free throws? Who wrote this one up? All right, Jordan, I guess I don't need to explain this one because it's literally reading the chart, right? The number next to 3 is our answer. Nice job on part A. Part B asks us, okay, this one's a little bit more complicated because now we're asking for more than 2 free throws. Who wrote this one up? Caitlin, do you want to explain how you got this one? Perfect, right? So I think you added up the last 4 and we got 0.821. Very nice job there. And then part C, we wanted to know the probability of not making exactly 4. Mateus, do you want to take us through this one?
Yeah, I just saw the probability.
Perfect, right? So this is an opposite one where you subtract whatever probability you're finding the opposite of from 1. All right. Any questions on A through C here? All right, so it's not too bad. It's literally the same thing we've been doing, except when we have a binomial situation, we have to figure out if it's binomial or not. And we also have to go through Minitab to get the distribution. But once we have the distribution, everything works the same. All right, let's flip our page over and we're going to talk about something slightly different for a little bit. Okay. Whenever we do these questions in Minitab, sometimes the probability distribution isn't going to look as nice as the questions before. For example, in your quiz, I gave you a probability distribution and you had to find the mean. But usually in the quiz, it's only like 4 rows that you have to multiply and add up, right? In questions like these with binomial random variables, sometimes there's like not just 6 things that we have to look at. Sometimes it's like 0 through 50, okay? And you'd get a big probability distribution and you'd have to find the mean of 50 different rows. And that's going to take a long time, right? Even trying to find the mean of this distribution is going to take a while because you're going to have to multiply every single one of these numbers together and then add those numbers together. And nobody feels like doing that, right? So in order to make things a little bit easier for us, what we're going to do is, what am I thinking of? Oh, we have formulas for it instead, okay? So instead of going through the big process of finding the mean, the variance, the standard deviation of all these different situations, we have formulas just for the binomial distribution that makes things so much easier for us. Okay, so if we're dealing with a probability distribution and we know that it's binomial, so we know it has to do with this section, and you're asked to find the mean, all you have to do is plug in this formula. Remember, n is the number of trials and p is the probability of success. So if you ever want to find the mean of a binomial variable, well, mathematicians found this formula. You don't have to multiply across and add down. You don't have to do anything. You just have to multiply the two together. Okay. Same thing with the variance. By the way, this formula is written kind of weird. It's sigma squared with an x on the bottom. Okay. This time, if you want to find the variance, multiply the trials times the probability of success times this 1 minus p. Okay. Actually, does anyone remember from Friday what 1 minus p represented? It's the probability of something, but it's not the success. Okay. Yeah. The complement, and the complement of success is failure, right? So if I want to find 1 minus p, that's literally the probability of failing. Okay, so in order to find the variance, you do the number of trials times the probability of success times the probability of failure, which is 1 minus p. Okay, finally, to go from variance to standard deviation, you just take the square root, right? And I know this formula looks wacky, but this literally is the square root of the variance. Okay, so same thing as always, variance to standard deviation, just take the square root. Okay, now when it comes to these formulas, I do want you to memorize, yeah, I'll have you memorize these. Okay, so for the test, I want you to either memorize them. We'll probably do a note card again, so you just have to remember to write these on your note card. But let's just go through example using these formulas so we have a better understanding on how to use them. Okay, we have the probability that a new car of a certain model requires repairs during the warranty period. And this probability is 0.15. Okay, we have a dealership that sells 80 cars, and X is going to be the number of cars that require repairs. Okay, this one's asking us to find the mean and the standard deviation. Okay, so one thing we can do is type this in a Minitab, get a list of numbers 0 through 80 with their probabilities, but that would take way too long to find the mean and standard deviation of. So let's just go ahead and find the formulas. Okay, first of all, what does success mean in this situation? Remember, success is whatever we're interested in or whatever the variable is talking about. Requiring a repair, right? If X is the number of things that require a repair, what we're interested in is a car requiring a repair. Okay, and I know it sounds weird that a success is a car needing a repair. Success doesn't necessarily mean a good thing or a bad thing. It's just whatever we're interested in. So if we're interested in a car requiring repair. That's what we want success to be. Okay. Next, we have to figure out what the number of trials is. How many trials do you think we have here? 80, right? We have 80 cars. We're looking at each of the 80 cars. Looks like we have 80 of these cars. And P, remember, P is the probability of success. And the probability of requiring a repair for each car is literally in the question. It's 0.15. Okay. So let's go ahead and figure out what the mean is. Okay. So finding the mean. Remember, the formula for the mean is mu with an x on the bottom. Okay. And looking up above, the formula for the mean is n times p. Okay. So all we literally have to do is plug in the values for n and p. So 80 times 0.15, multiply those together, we get 12. And that's it. So whenever we're dealing with a binomial random variable, it's super easy to just find the mean instead of like going through all of that stuff we did for the quiz. All right. The next question wants me to find the standard deviation. Well, in order to find the standard deviation, first you have to find the variance, right? You can't find the standard deviation without knowing the variance first. So let's go up. The variance formula says sigma squared x is n times p times 1 minus p. Guess we have to plug in again, right? N is 80, p is 0.15, and I'm multiplying by 1 minus 0.15. I like to do parentheses first. I know you can do this in your calculator in one shot if you have one of those fancy ones, but usually I just use my phone calculator. So I do the 1 minus 0.15 first to get 0.85, and then you can multiply the three numbers together to get 10.2, and that's your variance. Okay. Now, we're not done the question yet because the question's not asking for the variance. It's actually asking for the standard deviation. How do I go from variance to standard deviation? Square root, right? So you take the square root of the variance, square root of 10.2. Well, that ends up being 3.19, and that's your answer. All right. Any question on example 3? All right, so binomial random variables, they're kind of tricky figuring out if something is one or not. It's kind of tricky figuring out the Minitab commands, but once you have that, it's literally the same thing that we've been doing, except we have a few extra formulas. All right, any questions